this is the outline of my 3 lectures. I hope I don't scare you right off, but I wasn't able to do without a very introductory lecture at the beginning. That would be this one, and so you will see more muons coming on as we proceed on lecture 2 and lecture 3. Here I will introduce very briefly superconductivity. Here I assume that some of you don't have superconductivity as their major topic, right? Is that so? No. Okay. And I'm sure that in the audience there are people who know more about superconductivity than me. It will be a tale of 3 length scales. And 2 length scales are presented in the first part. And we heard already from Martin Manson that whichever technique, it's always a matter of understanding what's the length scale and what is the time scale. And here we are concerned with the length scale. So London, penetration depth, and coherence length are the 2 main things.
Roberto.
Yes.
Your mic.
Sorry. Yeah. I hope that my voice is strong enough, but yes, probably. Yeah. Okay. You hear me better? You weren't complaining. You already were falling asleep. So, superconductivity is this thing. It started off in 1911 with the discovery of Cameriones, who found the disappearing resistivity in mercury while he was studying the then highly topical subject of resistivity in metals, right? The beginning of the exploitation of metals. And this is how elemental superconductors, which are the things that Cameron always stepped upon, stumbled upon, are distributed among the periodic table. And you see that they run pretty much like 50% of the periodic table. And, well, it's not a surprise because the largest part of the periodic table is metal, according to chemists. Then physicists start applying pressure or something, doing things, and discover that things can change a bit. And besides that, we are dealing nowadays with compounds. So we start with these materials, and you start from a non-superconducting compound like copper, and you get the cuprates, which are very interesting superconductors. By the way, if you look at these tables that I just picked up from the internet, you can find different versions, and for instance, some materials are missing there and being present there, and vice versa. So, I mean, this is just a broad overview. I'm not claiming it. Carbon could be, I don't know, diamond under better conditions or very high pressure. I don't know. So, why superconductors? First of all, I have to tell you why these are interesting. But the first thing is, of course, that you can make strong magnetic fields with them, and it's important to do that, because if you wanted to do the same 10 Tesla field that you have inside my magnet in the lab with a conventional current, you would draw probably the power that feeds the houses in Abingdon or something like that. And an example of that is CERN LHC, where they have some little less than 8,000 superconducting magnets to run the machine. And actually this is important because it means that for a decade more or less, while LHC was in construction, this was by far the largest industry connected with superconductivity, right? It was 90% or 80% of the superconductor industry concentrated in making this instrument. Then the next step in this sense is probably just finished. ITER, TOCAMA for control fusion. There you have to suspend a plasma by magnetic levitation inside a very hot machine. So you have this superconductor inside that inside an extremely hot source. And then the other large industry is MRI, of course. If you want to have your scans without cutting through your body, most of them rely on NMR imaging, and that is based on superconducting solenoids. So it's always about magnetic fields. Then there is another possibility, which is energy, but that has not really been employed extensively up to date. But there is another possible application that is coming, that is quantum computation. This is the existing IBM quantum computer. You can apply for computer time there. And it's based on plasmons, and plasmons have dissociation junctions within, so superconducting. And the idea is that if you have to replace conventional 0 and 1 bit by superposition of states, with the advantage of making intensively parallel calculation because you're doing at the same time the two bit values, you have to have variable, solid, macroscopic quantum states to base your computer on. So this is the reason, is that yet another reason to study superconductivity. Superconductivity is one of the few real examples of macroscopic quantum coherence states. And I will briefly tell you what that means, remind you what that means, starting from the fact that metals are also metals. If you look back at the beginning of last century, the explanation of metal was the great success of quantum theory, and it tells us that electrons in metal are in a quantum state. And the quantum state, if you really think carefully, must be a many-body function, which is a quantum state, a coherent quantum state. But then we know that in metals, we can also forget about their interactions, treat them as independent particles, as k-states. And actually in that picture, we go back to the classical picture, we see them scattering around all the time against some kind of having collisions, and decohering in the terms of quantum computation, right? So normal metals have this kind of resistivities. The important parameter here is the coherence time, the scattering time, tau or Drude, you want to do the model, and that's typically 10 to the minus 15 seconds in metals. And you go down to superconductors, resistivity goes to 0. And if you work it out from the decay, the slope of the B field in my magnet in the lab, it will disappear in 10 to the 10 years. That's typically 10 to the 17 seconds. So this is a scale of the coherence. NMR and USR, you heard about relaxation times, right? So nuclear spin probes and new ones as well are somewhere in between. They decohere slowly, so that you can measure them, and the decoherence is in the range 10 to the minus 7 to 10 to the few seconds. Metals are one end, and superconductors are the other end, right? And this is another why superconductors, material science. This is just out of Wikipedia, and I won't stop here now. I will come back later. You see how rich this diagram is. This is a timeline, and you have to remind yourself that the first 80 years are just 2 steps, and the rest is dilated. And you see how many families come about, and how many attempts to bring superconductivity, which is a low temperature feature, to room temperature application. So we saw resistivity that goes to 0. Many of you know very well that the second signature of superconductivity is some sort of perfect diamagnetism. And we shall now review that because it's slightly different than perfect diamagnetism. If you have a perfect diamagnet, like for instance, it is implied by the fact that you have 0 resistance. So if you in any way produce eddy currents, they will survive, say, forever or for a very long time. So if you're doing that, you can devise the following experiment. You assume you have a perfect diamagnet, a perfect conductor, still below a certain transition temperature. So you start above the transition temperature with no field. You cool with no field. So you're now cold with no field. You apply a field, and by Faraday's law, you can't have any variation of flux in time because there's no resistivity, so the electromotive force has to be zero. It means that there must be a spontaneous current that circulates in the opposite way to the one that is producing the field to shield the field inside. This happens in a superconductor, in a real superconductor, and in this putative material. But the difference is, if you now do this other experiment, you have a field already above this supposed transition temperature, so the actual transition temperature of the superconductor, and you cool down in the field. Then the perfect conductor sees no difference from a Faraday law point of view, and will still have the flux inside. So it means that if you stop the current outside now, it will produce a spontaneous current and make a magnet. Contrary to this, the real superconductor expels the flux immediately as the transition temperature is reached. So the real rule is not obey to the Faraday law, but is don't have any flux inside. So this is the rule. So the superconductor is really a different state, and this is the quantum nature, quantum coherent nature of the state. And here is what you get experimentally. This is just one sample picked up of the literature like that when making the slides. It's a couplet, and you can see that you can zero field cool it according to the first procedure I showed you. So cool in zero field, then apply the field, and you get a negative m over h. You can follow it with temperature. Or you can do the other procedure, field cool it, and you still have sorry, zero field cool it is the red, field cool it is the blue. You still have an expulsion of flux, with subtle differences that have to do with spinning of flux lines inside the superconductor. But this is, I call it extrinsic physics, right? So the next distinction I have to talk to you about is that you don't have only the elemental, but you also have the compounds, and they often are of a different type. The superconductors I've been talking to you about are type 1, and they behave like this. You can see it here. If you apply a field, the transition, the zero resistivity transition that you see here in zero field shifts. Right? And this is an example where it shifts quite readily, so you can map how it shifts. And you have this curve, which is a phase diagram of the superconductor. This phase is superconducting, and outside here it's normal. But you can have other curves, and this corresponds to this kind of susceptibility, if you wish, that is dm by dh or m over h. I plot here m with a minus sign, so as I increase h, I have to increase minus m, and until a point where it drops, which corresponds to the maximum field that I'm going up this way. But the second type of superconductors is like this. They have a minus m versus h curve that obeys the same Meissner effect here, the expulsion of the flux, and then it goes down like this. So here you still have shielding currents, but they're less effective. And the explanation is that they are inhomogeneous. They don't regard the entire sample. They are localized somehow and inhomogeneous. We should see a little bit more. We know how it is. It's flux lines, and you can see them like sprinkling iron powders on top, like people did in the old times, and you can use a scanning screen microscope on YBCO and see these blobs, which are flux lines. So the field is strong where these black lines are, and you can see here the plots, right? And they mean that there is a circulating countercurrent. There is a screening current outside the sample, but then circulating countercurrents around these vortex lines, and this explains the homogeneous state. So I'm coming now to this. I lost my watch, but anyway, to these three depths that I have to introduce to you in order to tell you what muons will see and how they will measure these quantities. The first controls how the magnetic field penetrates in these samples. The second controls the scale over which the wave function can extend. And we shall see that a little bit better. And the third, of course, has to do with scattering with impurity, which was already there in the method to begin with. So now I will have to tell you about the simplest way to treat the field dependence of a superconductor, which was devised by London first half of the last century, together with his brother Heinz, Fritz and Heinz London. And what they did was to really go deep into the understanding of what a quantum wave function was. Actually, this is really founding work in that direction. And I try to sketch here a way of reasoning which is perhaps not the direct one, but it's the summary of what he thought. They confronted incoherent methods with the scattering with quantum coherent superconductor, thinking of the current density, right? Which is like that. Density of carriers, charge, velocity. And if you don't have any power supply in a method, you have average of P equals 0. That means average of V equals 0. That means J equals 0. Of course, you don't have any current. So now, if you have a quantum coherent superconductor, you can think of applying a field to that. And the point that Chris London was thinking of was, since you're in a quantum coherent state, you should still conserve linear momentum. So linear momentum can't, if it was 0 at the beginning, can't be different from 0 after. You simply apply the magnetic field, right? So what do you do when you apply magnetic field? What you do is to do the so-called minimal substitution. Instead of treating P, you substitute P by P minus charge times the vector potential. So now, if this has to be 0, then this is a very crude, short version of his thinking. But then the average of V, of MV, must be equal to minus P over MA, right? This condition, you simply put P equals 0 there, take the averages, and this is what you get. Then you feed this back here. This is actually average V, and you get an equation like this. J must be equal to ME times minus E over M. This is the formula. So this is the summary London equation, right? So now what do you do with that? With that, what we are going to do is to feed it back into Maxwell equations very briefly to see what must happen on the field when you have a superconductor, because then we have muons, and muons will feel this internal field. So we have to check that. And if you do that, from here you get this equation through the Ampere law. And this equation, let's first have a look at it. It's very simple. It tells us that the Laplacian of V is proportional to V through a constant. The Laplacian of V is 1 over, is the derivative with respect to twice a length scale. So it must be the field divided by the square of a length scale. So this is the square of the length scale. And it's the length scale that controls how V penetrates the sample. So we call it 1 over lambda squared, right? And this defines lambda, simply because of dimensional constraints. We shall check later what is the dependence of lambda on these parameters and what that means, but this is a very basic thing. So let me just remind one thing. For London, at his time, so this is lambda, so it's the inverse of this, square root of, right? From lambda squared to lambda. So m goes to the top. And m is the electronic mass, right? And n is the electronic density, and E squared is the electronic charge, like in the original curves. We now know that really m is the mass of what is conducting in a superconductor, which is a Cooper pair. So it's twice the effective mass of the material. Then E is 2E squared, but luckily also n is the density of pairs, so it's half the density, and if you put together all these two factors, you get exactly the same. So it's the same both if you're looking at electrons or at the Cooper pairs. And incidentally, if you do the same equation on A, since there is this very simple linear relation, it turns out to be the same equation. this poses a problem because A is a field that we don't know. We know it apart from a gauge, right? So there is the question of the gauge symmetry breaking in superconductivity, which is rather subtle, and I'm not sure I have time to go in. But the answer is that this is not really the final version. This is the simplified London version. There will be a slightly more complicated one. So how do we actually get there? I'd like to show you because it's so easy. You take the curl of the Ampere law. So stationary currents, you have no Maxwell term, there's no change in E field, and you take the curl of that. And there is a vector identity that tells you that the rotor of the rotor is the gradient of the divergence minus the operation, right? And it's very easy because the divergence of B is 0. There are no monopoles. We learn at school. And so this goes away. And then you do the rotor of the right-hand side times mu. So essentially the rotor of J is the rotor of A, which is again B. So this is what you get. You couple this constant and that constant. The minus side goes away. And here you get exactly the equation that I was writing before. Right? And this is 1 over lambda squared. Like that. So it's very easy. It's not difficult to get done. And what does that imply? It's simple. It means that we said screening curve. But let's see that directly. We can see it directly from the Maxwell law. You have the rotor of B, which is equal to the density. Right? So now, assuming you have a vertical field like that, it means that you had some sheet of current right here that was producing it. And then this turns superconducting. So what happens is that it has to obey to that, and the way it has to obey to that is, by also obey to the other equations that I showed, is that this must be the kind of solution. This is a guess. And it's right, because if you take the rotor of that, it's very easy. You take the derivative of that field on Z, and there's only one component, which is the X component, that has a non-zero term. That's like that. And that has to be J, essentially. So you see immediately, the J is something that disappears like an exponential, and it's also in the opposite direction of X. So as it is written there. So if the current here producing the green field was like that, the shielding current is like that, and it produces a field that shields, right? So it's very easy. And if you have now a thin layer, it goes on to that. It's just straightforward. So what you could do if you're really winning is to check that this is the rotor of that this is the proper solution, that they obey these two equations and that equation. But okay, it's a little bit more of those calculations. Now, for this lecture, how much time do I have?
25 minutes.
25, okay, so I'm probably going even faster than I thought. I will have to go into a little bit more detail. Now, I will have to mix a little bit of introductory talk and a little bit of material properties. So, interesting materials happen to be anisotropic metals. So, what you do when you have an anisotropic metal, instead of having an effective mass, you get an effective mass tensor. So it means that currents will flow with different lambdas in different directions. It's a bit complicated, really, if you want to do it properly for the general case. But the simple case is when you really have currents only flowing in one given direction. Like, for instance, if you have a semi-space like here, and you implant muons perhaps just behind here, so you're not interested in what happens in the other borders, you're just looking at the surface. And you have a single crystal and you can rotate it and explore different directions for this right curve. So you're expecting in one direction to have that, in another direction to have that, and if you could turn the sample again, you could get the third direction. Now, we will be talking about YBCO, the cuprate, which is very anisotropic. There's essentially two equal M stars in one direction in a plane, and a very different one in the very much bigger one in the third direction. But we are exploring the fine difference in the plane, because the system is orthorhombic, so it has a fine difference. And this is the experiment by Kiefer et al. Some time ago, and it's done with low energy muons, so I'm anticipating what will be shown later. But here is above TC probably, or just in the first layer outside, but I doubt it because it's not that. Then if you implant muons, you have two things. The first, which is important, that you implant them further in, so you're exploring this exponential decay, and you see that the frequency goes down as you go further in. This is the distribution of muons as a function of depth. The second thing is that the distribution is not aligned, and so you get some damping on top, but that's not important here. So you can map the average frequency and plot it for one current direction, for the other current direction, and you can spot actually a small difference. So this is a very nice textbook case experiment, right, for this thing. So I'm now switching to different perspective towards superconductivity in order to introduce the second characteristic length, which is the coherent length. And there are actually two ways to do this, and we should briefly see in the following lectures also the other way, which is proper way, but from microscopic theory. This is a Landau model, and you heard already about Landau. If you didn't hear in your curriculum in your previous experience, you heard for sure in the magnetic lectures about the Landau models. The Landau models theories are like this. You just want to have a thermodynamic theory to describe a phase transition. And here we have a phase transition because above TC there's no superconductivity and below there is. So this is the kind of way you do. You take an order parameter, which here is called square modulo of psi, and it comes like in the magnetic case, in the second power and in the fourth power. It comes in the even powers because there's no difference between applying, having the other parameter in one direction and the opposite in the generic case, apart from very special ones. Then there is a term that is connected with magnetic energy. And what I'm inviting here is actually a free energy density. You can see this from the shape of this magnetic energy. It's just an energy density. And this is really the superconducting energy equals to the normal energy, free energy, plus something that must be negative below TC, so that this state is favored below TC, and must be positive above TC, so this will be chosen above TC. And this is done simply by supposing that the constant in front of here has this form. It's clear that this is positive above TC. Sorry, yeah, this is positive if A is positive above TC, when T is larger than TC, and switches sign, goes to 0 and switches sign at TC. So, without going into the detail of mathematics, if you have seen this kind of theory, for instance, in magnetism, you know that it gives rise to another parameter. This is mean field, so it always gives rise to this kind of other parameter, which is proportional to Tc minus T to the 1/2 mean field critical exponent, and is 0 above Tc and different from 0 below, right? And has a characteristic. It's a second order phase transition like this. So, one thing that we can immediately tell from here is that we know that if we push the field above BC, HC or BC as you wish, this superconductivity will disappear. So the difference between these two will be exactly compensated by this term when we get to the critical field. So it means that this is the order of magnitude of the cohesive energy of the condensation energy of the superconductor. Right? This is the gain that you have to have a superconducting state if you're below that field. So it's of order field squared over to mu0. And if you work it out, for instance, for niobium, it turns out to be of the order of 1 microelectron volt compared to the typical scale of the metal, which is electron volts, not one, but more, probably. So it's a huge difference. And here was the original puzzle. How can there be a state that survives in a metal that has such a large energy scale with such a tiny condensation energy? So for the following, I will forget about the non-linear term, the fourth order term, really. Linearize this equation. It means that what we're saying is it's strictly valid only very close to TC, but in practice it's valid in general. You can extend it, and anyway we are just making sketches. And I want to go one step forward. Nico Landau said. So the first example of this kind of Landau type theory with the term that I'm introducing now, which is a gradient, the possibility for the order parameter to be inhomogeneous, was actually dates back to very long before. It dates back to Van der Waals. Van der Waals studied this problem thinking of studying phase transition between liquid and gas. Everybody understands this. And then he thought, I have a vial with liquid on top, gas on top, vapor on top, and liquid below. And how does that happen? Does it want to have an interface, a physical interface, or not? Or the interface is unfavored? And the way to study that is to introduce a term which is proportional to the gradient of the parameter. And Van der Waals did it and discovered when it was stable to have this coexisting layer on top, right, of simple fluids. And you can do the same with superconductors. You have to introduce a term which is proportional to the gradient of the order parameter, which is psi. I didn't underline it enough, but this psi is a complex of the parameter. This is a special thing that you have to do. It cannot be a real order parameter. It has to have a modulus and a phase. And here you're introducing the gradient of that. And it's the cost of varying the order parameter. So again, we will do just the dimensional argument, right? So you take a ratio of, say, this to that energy. And that contains is made out of a ratio of the order parameter squared over the gradient. And this has the dimension of a length squared, right? Because there's 1 over length squared here in the denominator. And the reversed constants in front of these terms are like this. And this has to be a length squared. And this is the coherence length squared. The Landau definition. So what does that mean? Exactly like in Van der Waals' example, take a normal metal and a superconductor and put them one on top of the other like that. And it would be favored to have an interface if the total energy gain is negative. I mean, if you gain energy in stacking this thing together. And what are the energies? On one side, you are paying the energy of making this coupling. And this energy loss is proportional to the condensing energy over the volume, which is proportional to the thickness of that layer. And the thickness will be how fast the order parameter can change from the normal to the superconducting state. So this is a thickness psi. On the other side, you're gaining energy for the fact that you're expanding the magnetic flux over a different energy state, which is lambda. So if this is larger than that, then you're gaining energy. Turns out that you have to have lambda over psi larger than 1 over square root 2. I don't know, so explaining that why is that, but essentially it's like that. So if you're comparing these energies across the interface, you're explaining why you can get inhomogeneities in type 2 superconductors and why you can't get them in type 1. It must be that in type 1, and it turns out to be that in type 1, lambda is smaller than psi, so you're losing energy through this scheme, you're not gaining energy by making an interface. Whereas here, you're gaining energy by making interfaces, and this means that if you're clever enough and make enough interfaces, you can even getting more field. So you can exceed the critical field that I was talking to you before. And actually, in type 2 superconductors, you have other two critical fields. The field where the flux starts to penetrate in the sample, and the field where it stops to penetrate. So now, am I ready?
7 minutes, 8 minutes.
Okay. So, I don't want to do any hard math, but what do you do with these free energies that I've been talking about? What you do is you minimize them. So you choose, for instance, the order parameter as a variable thing. You do a variational calculation, and you choose the order parameter that minimizes them, right? So if you do it here, you have now a new degree of freedom. So you have also to vary the gradient of the order parameter. That's an independent variable. Essentially, it's psi. It's the scale over which you can vary that. And if you do this variation, you get out this equation. This is done in the linearized version, so it's easier. And if you look at this equation, it looks just like a Schrödinger equation, right? Well, it's a trick. It's because I called the constant in front of the gradient term, I called it h squared over 2n. I played a bit with that, but that's exactly what Hinflug did. And the coefficient here becomes the eigenvalue of the wave function. So there is now we have a complex wave function. It's not out of a quantum theory, but we have a complex wave function and a Schrödinger equation, and we are trying to believe that that will describe the wave function where the electron pairs will condense. And a little bit more I will say when I will touch on the CS, on the incorporation reference here. So, okay, so this, I haven't derived it, it's simple. This is the solution that you get when you minimize that. Now, let me take this. If you do that in a field, you have to go from here to the substituting something like the minimal substitution and then adding the magnetic energy. So there is a standard way of writing the free energy in a field, which is this. Now we have to minimize with two parameters on top of the order parameter. One is the gradient of psi, like here, and you will get a new Schrödinger equation, which will contain the magnetic field. And the other is minimizing with respect to A, because A is not an external field, it's also the field of the supercurrents. And the field of the supercurrent is a major player inside the superconductor. Right? So you have to treat that at the same level as the order parameter. If you do that, the only thing I want to tell you is that you get two equations. The first is, again, Schrödinger equation with a field. The second is an equation for the currents. And it's a little bit more complicated, but not so dissimilar from the London equation. If I write here the London equation, you see it immediately. Think of now of a homogeneous order parameter, so this term goes away, like in the London case. And this and that are essentially the same. Simply, n is psi, square modulus of psi, which is what you would expect, right? So this tells also what to do with psi with fields. You have to use it to calculate the London penetration depth. Okay, so this is the last slide of this part, and I promise much more universal results in the second part to go to still have a bit of theory. So it is convenient to have a normal superconductor interface when K, the kappa, which is, I didn't give the name, but it's the ratio, dimensionless ratio of these two parameters, these two length scales, is greater than 1 over square root 2. And if that happens, you could have, for instance, field effects inside the sample. Imagine that you have one field line, very strong field line that penetrates inside the sample. Then you have, around this field line, you have two length scales, lambda and psi. And if you want to have superconductor outside, you have to have B decaying, like we have seen before, right? With lambda. And of course, where there is a field, it can be a superconductor, so this must be a normal point. But this is a defect, and then the rest is a superconductor. So it will recover superconductivity within psi. So it means the picture is that you have a vortex core, which is normal, and around it you have supercurrents, and then the field is sloping slowly. And the field is sloping, it's going to zero towards zero on its own, at its own pace. Whereas the other parameter is recovering before. It must be that psi is smaller than lambda, otherwise this game doesn't work. So the only point to take home now, before next lecture, is how do you modify the London equation in order to describe that. It's very simple. It turns out that the London equation had zero here, the London field equation, right, had zero here. It was population of B equals to 1 over lambda squared B. Now I've taken all the B part on the left side, and on the other side I've put phi 0 delta R. Phi 0 is actually a flux quantum. It means that it's not really important what is the field here. The important thing is that the magnetic flux that you intercept if you take an area around that is one quantum. And this testifies the quantum nature of superconductivity. It really is one quantum, and the one quantum is h over 2e. And this, it is really 2e in normal conventional superconductors. So it tells us that electrons go 2 by 2 there in pair. And okay, and if you simply add, you see this is b over a length scale squared, so exactly like that. So this is the equation we will have to think of. So the last slide before moving to the next one. The next lecture, we will talk mostly about what happens when you develop this new inhomogeneous state, which is the flux line lattice, where typically you have a periodic condition like this. I mean, I didn't plot them all, it's a regular lattice. And increasing the field, you shrink this lattice and you go on to the closest packing that you can get. After that, you destroy the superconductor. And this is what we will read for the next lecture. And I promise many more muon results. The question is, what will muon detect in that condition? Right? And we will work out that and show examples of that. And how to really do that when you have data. Okay.
Yes, thank you for a very, very nice introduction to superconductivity. So coming from magnetism background, I was a little bit wondering about the superconducting order parameter. So in magnetism, you can always measure the order parameter. So you said that in superconductivity, it is related to the concentration of the Cooper pairs.
Yeah.
So can that be measured experimentally?
Exactly. That can be measured in several ways, in which we shall see them in the next lecture. But one way is here. If you bear with me, n is psi squared, but this is the ingredient of lambda, where I have one, probably. Just here, I don't have lambda. You remember lambda, I worked it out before, it's m, or here is one version, is m over mu0, n. So, for instance, if you measure 1 over lambda squared, you directly get something proportional to n. So that's you don't get psi, you get psi square modulus, right? There are other ways of getting the phase, and that has to do with the gauge invariance that I haven't been reading.
Okay, thank you very much. That clears it up.
And there will also be ways to measure psi from the data, although probably with the same caution that Martin has put to explain how to measure diffusions. I mean, you have models, you have data, you try to contrast them, and you have always to keep in mind that you might not be seeing exactly what you want to see.
I mean, to to add to the answer of Roberto, USR is really the technique to measure this superfluid density. There's no other really technique that can measure the absolute value of the superfluid density. Measure the temperature dependence of the superfluid density. To have the absolute value, USR is the technique.
I must say there are other techniques, but yeah, they have their own problems and pretty big. One technique is that of measuring electromagnetic parameters, like for instance cavities and lambda fluid effect on the cavity. And there you have to do some further modeling, and it's probably hard to get. There are subtle experiments to do calibrations so to get the absolute values, but USR is, you will see more direct.
Other questions? Okay, so everybody will read carefully the lecture of Roberto.
No, because I may try to.
Oh yeah, there is one question.
In oxide semiconductor, superconductors, the muon would sit close to an oxide, right?
Yes, that's a very interesting problem. Yeah.
And it would distort the lattice, for sure. Wouldn't that change the coherence around?
Okay. This might be a very subtle question, so let me answer the straightforward answer, 80% or 90% answer. No. You will see that the most used way of measuring these parameters is not in the way I explained here, but in through the flux lattice. And there the trick is that it doesn't really matter where the muon ends up, because the flux lattice is incommensurate with lattice. So where the muon ends up doesn't really matter. Then the subtle part is that if you have very flimsy superconductors, then the muon might locally interfere, and the muon is measuring locally. So this might be an issue, and you are certainly right there. But that I know of, there are attempts to think about that in the case, for instance, of type superconductors, where superconductivity is very fragile, but in normal superconductors, I'm not aware of any case where that is an issue.
There are some samples where magnetic interactions coexist with superconductivity, and what should we do with them?
Yeah, okay. Once again, I hope, is this still on? No, this doesn't work. What's this one? Yeah. So if I go rapidly back to the beginning, I show you that, okay, that's really bad. That it's part of my third lecture. But anyway, I take the chance to say something here. There are, again, two sides to that. One is that certain materials seem really to have that as a feature, a strong feature. So the question is and USR is pointing very strongly towards the fact that with very small coherence length, you can host a state where magnetism and superconductivity can coexist very nearby. We should talk about that. And this is perhaps an interesting question, but I'm not sure we can answer the question, which is whether this is really electronically intrinsic, or whether it's determined at higher temperature where you measure samples and they are finely homogeneous. It's difficult to say. But it is an issue that is worth thinking of. The other problem is when you have a superconductor that has impurities, magnetic impurities. So in that case, it's really a problem. And this has been, we will see, it's been the case for the pnictides. Very often in the pnictides, you haven't been able to perform the same kind of experiments that we are used to because of these nasty and ineliminable, not always lucky, but in certain cases, ineliminable magnetic impurities. So you have to apply a field, and you're magnetizing your impurities depending on the field, so you're altering. So that's
Okay, so I think, thank you again, Roberto. We have to move on.